Okay, this is section 5.3, very short title, enthalpy, but it's a pretty big, meaty section here. But luckily for us, the calculations we do are relatively simple. So the idea here is that we can look at thermochemical or thermodynamic processes occurring in two different cases. One, we're going to call it case one, is constant volume. And then case two is constant pressure. And it turns out if we look at changes, energetic changes occurring under these two different processes, we get two different results. So we need to go through each of them individually. So let's try the constant volume first. The idea here is that imagine we have a cylinder, which again would be just like a coffee cup, only this coffee cup has a movable membrane or a movable piston. Okay, and we're going to put a gas inside. So there's a bunch of molecules bouncing around in here. And what I'm going to do is I'm going to lock that movable piston in place. So I'm going to put little locking mechanism there so that it cannot expand, right? The piston can't move up beyond those 2 points. So its volume is locked in. And now what I'm going to do is I'm going to add some heat. Bunsen burner, right? We're going to add heat to that. Now, there are two ways in which that energy, which is coming in as heat, can be distributed. One would be to make the molecules inside go faster. So we would be increasing the thermal energy. The second would be for those gas molecules to push that piston up against the air, pushing against air pressure. And if that piston is locked into position, it can't do that anymore. It can only stay rigid. It can only stay there in that one spot. So that means all of the energy that is coming in as heat, as thermal energy, is going to go into the gas. And so what I'm going to do is I'm going to say the following. The change in internal energy of the gas for this constant volume case is going to be equal to the heat that we put in. Now, I'm going to indicate that this is the case because the volume is constant. Okay? So any heat that's coming in is going to go into the internal energy of the gas. The gas will have more internal energy. So that means its internal energy changes, delta U, that's a change in internal energy, is equal to the amount of heat that we're putting in because it's at constant volume. Okay? Relatively simple. Now, let's look at case two. Case two is constant pressure. Okay? Now, for the constant pressure, what we're going to do is we're going to take this cylinder and we'll put the piston right there, and we have the gas. And keep in mind, the atmosphere is pushing down on that piston. Air pressure, we call it, right? And now we're going to do the same thing. we're going to add heat into that gas. I'm just going to apply a Bunsen burner to it. Okay? And so here's what happens. We're going to get a physical change occurring. As we heat the gas, the piston will move up to some point here, right? It's going to move up by some height. Okay. So now the gas gets more spread out. It's over a larger volume. But we've pushed the atmosphere some distance, and it takes work to do that. Okay? So that means in this case, we've added heat and we've converted it to doing what's called work. Now I'm going to define something for this case called enthalpy. And I'm going to define enthalpy. The word is spelled E-N-T-H-A-L-P-Y. The word enthalpy, the symbol for that is an H. Okay? And I'm going to define it as the internal energy of the gas plus P times V, where P is the pressure of the gas and V is the volume of the gas. Okay? I won't explain to you exactly why we define it this way, but the result is the reason. It turns out if we define it this way, the results work out well. Now what I'm going to do is I'm going to go back and come back to our idea of what internal energy is. The change in internal energy, that was from the previous section, delta U, is equal to, meaning if the internal energy changes, the change comes from either adding or removing heat or doing work on the system or having the system do work on the surroundings, right? Those are the two ways we can change the internal energy. But now I'm going to go back to defining work a little bit more precisely. There is a specific type of work which is equal to negative P delta V. Okay, so this is the work of expanding a gas or compressing a gas. And it works for a cylinder. So if we have a gas in a cylinder, the amount of work is negative P delta V, where P again is the pressure of the gas, and delta V is the change of the volume of the gas, or the change of the volume in the cylinder. So now let's come back to this definition of enthalpy, and I'm going to change it a little bit. I'm going to say, suppose we have a change in enthalpy, delta H. Well, that would be the change in the internal energy. I'm just putting delta for changes, plus the change in PV, right? It's not obvious why that's the case, but mathematically it works out. Now what I'm going to do is I'm going to say we're in case 2, so we're at constant pressure. So that means the pressure can't change, but the volume can. Look at that picture down at the bottom again. See how the height is changing? So the volume of the gas is changing there. So I'm going to say for this case, for case 2, delta H would be delta U plus P delta V. So if the pressure can't change, it's a constant, but the volume can, then we would have a constant pressure times the change in volume. Now I'm going to come back over here to our definition of internal energy. The change in internal energy is the heat plus the work, but the work is negative P delta V. So now I'm going to substitute everything in here. Delta H would be delta U, which is Q plus W, which is Q minus P delta V, right? Because W is minus P delta V. But delta H is delta U plus PV. So I'm going to add P delta V. And look what you get. The negative delta V and the positive delta V cancel, and you just get Q. So in other words, delta H is equal to Q, but only if we're at constant pressure, because if we're at constant pressure, this P here is a constant. If we're not at constant pressure, if we were at constant volume, for example, then constant volume delta V would be 0. So here we have a secondary result. In the case of constant pressure, so I'll put a little P down here, the change in enthalpy is simply the amount of heat that we're adding. Okay? So now, case 1, constant volume, case 2, constant pressure, we have two results that are relatively simple. So I'm going to sum them up right here as soon as I get some room. If we are at constant volume, we're going to claim that the change in internal energy of the gas is equal to Q, and to indicate that it's at constant volume, we put a V. If we are at constant pressure, then we're going to use this quantity here called delta H. And delta H would be equal to Q, the amount of heat coming in or out, and to indicate it's at constant pressure, we put a P. So all of that is really just a way of saying, look, we're going to try to make things very simple. If we're at constant volume, we'll calculate the change in internal energy of the gas. If we're at constant pressure, we'll calculate or measure the change in enthalpy of the gas. Okay? For the most part, the examples that we're going to look at in chemistry are constant pressure. Not always. There's some examples. For example, combustion is often done in constant volume. But many of the reactions that we would do in a laboratory, such as an acid-base titration or a reduction oxidation in a battery, right? Batteries, these are done under constant pressure. So it's more useful for us to tabulate and consider change in enthalpy than it is to tabulate or calculate the change in internal energy. So enthalpy is the key here to this section. This is enthalpy, change in enthalpy, delta H. Now, because the change in enthalpy is equal to Q under constant pressure, sometimes people call enthalpy heat. That's kind of a loose term to use, but sometimes people will say that. They'll say the heat of reaction or the enthalpy of reaction, the heat change in enthalpy of the reaction. Okay? Now, one reason that we use enthalpy, aside from its simplicity here, is that enthalpy, just like internal energy, are state functions. Remember we talked about that in the earlier section, 5.2, I think it was, the previous section. These are state functions, just like temperature and pressure and volume. These are also state functions. Now, the reason this is a V for volume, the reason this is important is because some properties or some variables are not state functions. For example, work and heat. These are path functions. And path functions, their values depend on how you get there. Okay? Whereas state functions, their values do not depend on how you get there. So we prefer in our calculations to use state functions. They're easier to analyze. So the fact that enthalpy is a state function is beneficial for that desire. Okay? Now, the rest of this is all about how do we calculate using enthalpy. So let me just make a couple of points. That the change in enthalpy, just like the change in internal energy, is equal to the final amount of enthalpy that a system has minus the initial amount of enthalpy that it has, delta H. So for a chemical reaction where A goes to B, right, we have reactants and products. The change in enthalpy for a chemical reaction would be the enthalpy of the products minus the enthalpy of the reactants. So I'll be more general about that. H products minus H reactants. And that's useful. So changes in enthalpy is what we're going to look at. So for example, let me give you a couple of examples of enthalpy changes. They can actually be physical or chemical, but here's an example of a physical process. It's a physical change. And that's the melting of water. H2O solid, ice, getting converted into H2O liquid. Turns out there's an energy change associated with that process. If I take 1 mole of ice and melt it into 1 mole of water, there's an energy change associated with that. And it's at room temperature, it's 6.01 kilojoules. That's the amount of energy associated with melting a mole of ice. And the energy change, we're going to use delta H to represent that energy change. The amount of energy it takes to melt a mole of ice into liquid water at room temperature, 25 degrees C. So let me put that this is at 25 degrees C. Is 6.01 kilojoules. And remember, kilos 1,000, right? 10 to the third. So this is 6.01 times 10 to the third joules, right? 6 kilojoules or 6,000 joules. So that physical change has an enthalpy change. There's an energy associated with that. And of course, you know it takes energy to melt ice, right? Well, there's a quantitative measure of that. That's how much energy it takes to melt a mole of ice. But we can also use it for chemical reactions. So for example, if we look at the combustion of methane, methane is the principal component of natural gas. We can combust it in oxygen to form carbon dioxide gas and liquid water. And it turns out there's an enthalpy change associated with that. The enthalpy change, again, at 298 Kelvin, or 25 degrees C, is minus 890.4 kilojoules. Okay? In other words, if you take 1 mole of methane gas and combine it with 2 moles of oxygen to form 1 mole of carbon dioxide and 2 moles of water, this is how much energy is released. The fact that it's negative means that it's exothermic. Same sign convention as Q. It's negative, that means it's exothermic. That means it's releasing 890.4 kilojoules of energy. Now look how much larger that is than melting ice. It takes 6 kilojoules to melt a mole of ice. But if you combust 1 mole of methane, you get out 890 kilojoules. So think about it physically. What that means is if you have ice and you want to melt it using the energy released from combustion of methane, 890, that's how much kilojoules is released from 1 mole of methane. It only takes 6 kilojoules to melt a mole of ice. So you could melt a lot of moles of ice from 890 kilojoules from the release of this energy from the combustion. Okay? So I'm going to show you mathematically how we do calculations here using enthalpy changes, using this combustion reaction. I'm going to rewrite the equation. Okay, I've run out of room over here on the right, so I'll write delta H is minus 890.4 kilojoules. Here's how we evaluate this. For this specific reaction, what we would do is we would say that if you have 1 mole of methane, the amount of energy it releases is 890.4 kilojoules. Now that might seem a little bit odd to say a mole is equal to 890 kilojoules, but in a sense we do that all the time. 12 inches equals a foot. An inch is not a foot, but 12 inches equals a foot. That's what we're saying from this equation. 1 mole of methane equals 890.4 kilojoules. So think about it this way. Imagine you have a little package of food. You would say, hey, you've got this little package of cookies that has 100 calories in it. 1 package of cookies equals 100 calories. That's essentially what we're saying here. 1 mole of methane, the assumption is that we're combusting it in oxygen, equals negative 890.4 kilojoules of energy. So I could write this in 2 different ways. I could say minus 890.4 kilojoules divided by 1 mole of methane. Or I could say 1 mole of methane is negative 890.4 kilojoules of energy. And those 2 ratios, we can use those in unit conversion problems. Or suppose I said for this particular reaction, let's use oxygen. Then I could say minus 890.4 kilojoules of energy is what you get when 2 moles of oxygen reacts in this particular chemical reaction. Or 2 moles of oxygen react, and that gives you minus 890.4 kilojoules of energy. So I can do it for either reactant. Likewise, you can do it for either product. So I could say minus 890.4 kilojoules of energy is what's released when you form 1 mole of CO2, or 1 mole of CO2 is produced when 890.4 kilojoules of energy, or enthalpy change, occurs for this particular reaction. And you can do the same thing for water. I won't show it for water, but it's essentially the same idea. There's 2 different ratios you can use. And the reason that we want to have these ratios is that we can use them in thermochemical calculations, as you'll see when we go through a sample problem and some of the homework exercises.